Check this out. We've got something really fun today. This is so amazing. Oh man, again? 1.2, Reflection and Stretches. We added and subtracted numbers inside and outside the function. Now we'll look at the effects of multiplying and dividing inside and outside the function. We're going to look at reflections, so where something is reflected over a line of symmetry. And we'll look at stretches, where something is getting stretched, either vertically or horizontally. The first thing we'll do is multiply by -1 outside the function. So it looks like this. Y is equal to negative f of x. Now, if this is y is equal to f of x, then we let f of x do its thing, and then multiply the result by -1, and then get our y value. So we're going to get the same inputs here, and the same thing happening. It's just that every one of these points will be multiplied by -1. So instead of this being 0, 1, we'll multiply it by -1, and that would be the f of x values, and it will become -1. This point here at 2, multiply by -1, it becomes -2. So the transformed graph looks like this. Now these are both written in function notation, so I'm not seeing any quadratic here, any x squared term. I'm just using function notation to show the transformation. Now let's go actually find the new equation. So the old equation here is x squared plus 1, y equals x squared plus 1. So when we actually write out the equation that we can put in our calculator, we would have y is equal to negative f of x, and then I'll just replace f of x with its actual equation, which is x squared plus 1. And then I don't like the extra brackets here, so I will distribute in the negative sign into both of these terms. So our equation would be y equals negative x squared minus 1. And that makes sense. We could have just looked at this and also figured out this equation. So it opens down, it goes over 1, down 1, so there's no stretch here. And we know about stretches from 20-1. And minus 1, and we did that in 20-1 as well. Minus 1 meant the vertex went down here. Mapping notation. So we start off with every point x, y, and we're giving a map of where those points went. So nothing happened to the x's. That's why everything is still lined up here. So they remain x. But the y's we did change. We took all the y values and we multiplied them by -1. So this would be negative y. And what's the line of reflection? Now we like to make an equation for that line, so don't just write 0. You could write the x-axis, or you could write y equals 0. And that would be this line here that it was reflected in. We want to multiply outside this function by -1. So let's do that from the graph. If we're multiplying outside, we're only changing the y values. Nothing is happening inside the function. It keeps doing its thing. So multiply by -1. 0 times -1 is still 0. How about this one? -1 times -1 is now +1. 0 times -1 is still 0. And I'll try to find another, nothing really good. Let's just do this one. It looks like about here. And so that would become -2. So we'll go straight down, -2. What else can we do? Maybe this one, 5. And that becomes -5. All right, let's do this side. We've got here -3, and multiply by -1, that would be +3. And then maybe this point down here, -6 becomes +6. And now we can draw our graph here. and so we have reflected in the x-axis. Always put arrows at the end of your graphs. The computer doesn't need to, but you need to. Let's look at the equation. So if we multiplied by -1, then we'd have negative and then the original function. And we can clean it up a bit. We can get rid of these brackets. So how about negative x cubed plus 2x squared? Now, invariant points are points which do not change after a transformation. In this case, they're on the x, or they are the x-intercepts, so they would be here and here. So these are invariant. Variant means change. Invariant means unchanged points. So all the points changed except these two. When we reflected, they stayed the same. So they are invariant points. Now we want to multiply the inside of the function by -1. Now if we're working inside the function, we're changing the x values. Let's see what will happen. This is f of x here, and I thought maybe it would be good if we made a table of values for every point that we see there. So let's try that. We've got x and y, and let's go from -4 to +4. So we'll write down all the points we have. -4 is 3, -3 is also, and -2, 2, 1, 0, 0, 0, -1. Okay, now let's actually put in our negative now for our new x, y. So if we go and try to put in -4 into here, it's going to act like +4. So let me show you. If we try to put in -4, then negative times negative is positive. So what the graph is actually doing is taking +4 as its argument and returning the appropriate value. So what would be the appropriate value if we put in +4? So we just look down here. +4 should give us -1. And so that's what this will give us. So we tried to put in -4. It used to give us 3, but that doesn't matter anymore. -4 gets changed to +4, and +4, according to this function, gives us -1. Let's try another one. So -3. So -3 does the same thing. We try to put in -3, and instead it gets, these negatives get canceled out. And instead we're using the argument of 3. So we look down here. What is 3 supposed to return to us? 0. And we could keep going through here, but hopefully you see the pattern. If we put in negative, it's going to act like a positive here. So this will be 0, 0. Now this one won't change because you put in 0. And there's no such thing as -0. So that one just returns 0. So that one stays the same, it doesn't change. Okay, and then the rest of these 2, and then 3, and 3, and 3. Let's look to see how this appears on the graph. So -4, -1, and then these next ones are 0, and then this one's 1, and then 2, and then 3, 3, 3. Let's connect them because this function was continuous before. And there is our f of -x. Now you look at that and hopefully you can see that that has just been reflected in the y-axis. Let's find the invariant points. So those would be the points that do not change after the transformation happened. And that would be right there. There's only one, and it's 0, 1. the y-intercept this time. And mapping notation, x and y is mapped on 2. This time we're changing the x values. So they're all flipped, and the y's stay the same. That's why the y's are all lined up still. We want to multiply inside this function by -1, or in other words, reflect it in the y-axis. Okay, so this point is going nowhere. This will be our invariant point. This point here will be reflected around and show up here. There's this point here, this vertex. It's a bit below, so I'll just approximate it to be about there. And then this one is about there. Now coming up, our x-intercept here is reflected over to here. And maybe this point here. Almost 3, so almost 3 over here. Now let's do this side here. This point here will be reflected onto this side, and maybe this is about there. So let's see if we can draw this. This comes down, comes up, and comes down. And we'll put arrows at the end of our graph here to show that it continues on. If there is no arrows on a computer-drawn graph, then you assume it continues on. A computer-drawn graph that does not continue on will just have a filled-in or open circle at the end to show that it stops. Okay, so that's how this new graph looks. This will be f at -x, and that's written in function notation, just like that, just so that we can see the transformation. Let's actually find the new function, though, in terms of x here. So f of -x, everywhere where we see an x, we're going to replace it with a -x instead. So I'll use brackets to contain it so I don't forget to apply the exponents to the whole thing. And then I'll clean this up because there's lots of brackets here and that's kind of messy. -x all cubed is still -x cubed. And this negative here remains. And this -x squared just becomes +x squared. And so this is the equation in terms of x. What's the line of reflection? Well, it's the y-axis here. And you could say the y-axis, or you could say the equation of this line, which is x equals 0. But you can't just write 0 because that's not a line. 0 is a number. When we multiply by negative outside a function, this is called a vertical reflection in or over the x-axis. And when we multiply by negative inside the function, this is a horizontal reflection in or over the y-axis. Now it is possible to reflect over other lines, but in this course we're only going to be reflecting over the x-axis, the y-axis, and one other line of reflection that we'll get to later. Now, if there are no other transformations, then the invariant points are always on the line of reflection. So that's why the invariant points are on the x-axis when this happens and on the y-axis when this happens. But if we do a slide or translation with this, then those will be moved off of the line of reflection. Let's stretch this graph vertically about the x-axis by a factor of 2. About the x-axis means that this will be the line we're stretching around. So all of this stuff will be stretched up this way, and all of this stuff will be stretched down that way. So by a factor of 2 means we're going to multiply it all by 2, and that would be the y values because it's a vertical stretch. And so all the y values are going to get multiplied by 2, not the x values. So this point right here, for instance, -4, 3, stretched twice as tall is -4, 6. It's now up there. Now this whole line is up there. Nothing happens to it except it got stretched vertically twice as high. Next, this one, -1, 1 gets stretched to negative 1, 2. And so just connect these here. Now this horizontal bar here is now at 2. And here it is at 1.5. And that is not going to get stretched anywhere because it's right in the middle of where we're stretching. So that point will be invariant. Negative 1 now gets stretched to negative 2. So let's see if we can connect these. Okay, and then this horizontal bar here at negative 1 now gets stretched to negative 2. And here is our new function stretched vertically by a factor of 2. What is the equation of the transform graph? Well, we don't have this equation in terms of x's, we just have it in terms of f of x in its function notation. So all I can say is that the new one is y is equal to 2 times f of x. And that would be because it was vertical. We're working outside the function. We want to vertically stretch this function by a factor of 1/2. Vertical means the y value. So we're going to take each y value and multiply it by 1/2. Nothing will happen to the x values. Here at the vertex, nothing happens at all because 0 times 1/2 is still 0. This one, the y value is 1, so multiplied by 1/2 is 1/2. Let's go to a convenient y value. How about 4? 1/2 of 4 is 2. And we can't see the rest. The next one would have been 3, 9. 1/2 of 9 is 4.5. Let's do the other side. It is symmetrical, so I'm just going to use the same values I used on the right side there. And then we'll connect up everything here so we can see our new parabola. Put arrows on the ends to show that it continues. What is the new equation? Well, in function notation, that would just be in f of x. We could say that it is 1/2 outside times f of x. Now, again, this is function notation. I can't see the actual function. I can't see that this is a quadratic. I need more information if I wanted to actually graph this. And I actually have the information, so I can write this in terms of x. So let's do that. Y is equal to 1/2, and I'm just going to put what f of x actually is. It's x squared. So there we go. That's the function in terms of x. This is the function in function notation, and it's just showing the transformations, but it's not showing what the function actually is. Now you might say, yeah, why did you say stretch here? Because it's 1/2, so it actually looks compressed. So it's a good question. It may look compressed or stretched, but we're always going to use the word stretch to describe these transformations. Now, you could express this as a horizontal stretch or a vertical stretch, but we always go with the one that is easier. And let's see what I mean by easier in a second. But you could see this looks like it was stretched vertically down here, or compressed, but it also looks like it was horizontally stretched. You see, we could have thought like it was stretched out wider here. So express this as a horizontal stretch. We could take some guesses here. I'll write them in red. And the first guess that I typically see is just putting a 2 here. So a horizontal or a vertical stretch of 1/2, and then they think, all right, well, horizontal stretch of 2. Now horizontal stretches will happen inside the function. So that's why I'm putting it inside here. But if we multiply this in here, this is 2 squared and x squared, and this is 4x squared, and you see that this is not right. Okay, so that didn't work. The other thing that we could easily guess is y equals, well, if this one's a vertical stretch of 1/2, maybe it was supposed to be 1/2 inside here. But again, that doesn't work because when we square this, it comes out to be 1/4. And that's still not what we want. We wanted 1/2 x squared. So we need to do some algebra. Let's just mark this also not right. Let's do some algebra and actually find out what is the horizontal stretch. So if I had this vertical stretch, I'm just going to do some algebra and move this inside the squared function. Now, how do I do that? Well, if I wanted this to have a squared, so it could go under this squared with the x, I can't just square it. I also have to square root it to cancel that out. Now they both have the same exponent, so I can put them together. Just like this one here, they both had the same exponent, so I could separate them. So here is the square root of 0.5 and times x, and that would be all squared. And maybe you don't like decimals here, because yeah, maybe we could do a bit better here. This would be the square root of how about 1/2 instead? Because then I could actually take the square root of 1 and the square root of 2 separately. So then I could clean it up a bit more. So 1 over the square root of 2 times x squared. Now, what is this? So there's some sort of horizontal stretch here, but it's not very nice. This has a radical in it. So that's what I mean by easier. This is not easy. This is not a rational number. So for this question, although we could express this as a horizontal stretch, it's not as nice as going with this one. This is just a nice rational number. Now let's come back to this in a second, and let's look at how do we describe this in words? What kind of horizontal stretch is this? Horizontally stretch this graph by a factor of 2. That means that we're going to take each of the x values and multiply it by 2. Nothing happens to the vertex here, it stays right there. And again, just like vertical stretches, horizontal will be about the y-axis this time. So we're stretching this way and this way. This point here, multiply by 2, so it goes here. This point here, multiply by 2, goes here. And it's symmetrical on the other side. We'll connect these up. And whoa, missed that one. So here's a secret. Let's make that bigger. Okay, so there's our stretched graph. And what's the equation of this graph? So just like last time, we might try guessing. So let's start off with that, because it's a bit counterintuitive. If we have a horizontal stretch by a factor of 2, then most commonly a guess might be 2 inside here. This doesn't work. If we tried putting x as 2 here, we should come out with 1. So let's see, if we put x as 2, then 2 times 2 is 4, and 4 squared is 16, so that's not right at all. So, not right. So, we need to think of a different way, and think of how translations worked. They kind of worked the opposite. Remember going on inside here. If we wanted to move right, then we would say x minus. So the same thing happens with this stuff. This one's actually y equals 1/2 x squared. And so when we want to horizontally stretch by a factor of 2, we need to divide by 2. So when we're working inside the function, numbers seem to have the opposite effect than we'd expect. If we tried that same point here, 2 divided by 2 is 1. 1 squared is 1, and that is the point that we have here. So this is the correct equation. Now, what's the mapping notation? So we have x and y, and these are mapped onto 2x and y, because our mapping notation matches our verbal description. So if we had this point here, 1, 1, let's actually try that one out just to show you how it works. If we had the point 1, 1, then it should move to 2, 1. So we take the x coordinate, or the x value of the coordinate, multiply by 2. Nothing happens to the y value. And there we go. That's where the point 1, 1 went to. Now let's go back and take a look at this last question here, because I kind of left it without completing it. This one right here, how do we express this horizontal stretch? So the horizontal stretch is actually that thing in the denominator. Horizontal stretch about the y-axis by a factor of root 2. So that's how we would say this horizontal stretch. It's whatever's under here. We want to horizontally stretch this graph by a factor of 1/2. So that will affect the x values. -3 will become -1.5. This bar used to be 1 unit wide. Now it's only going to be 1/2 a unit wide. This was at -2 when it started to go down. Now that's going to be at -1. This one here is going to be our invariant point. Looks like 1.5, 0, because again, when we're horizontally stretching, we're stretching away from the y-axis here on both sides. This point was 1. That's going to be horizontally stretched to 1/2. Let's see if I can connect these. And this one here is at 3, so that's going to go to 1.5. Whoa. Okay, so that's our new transformed graph. What is the equation of the new graph in function notation? We don't actually have this in terms of x, so we have to use function notation in this case. Y is equal to, and this is a horizontal stretch, so that means we're working inside the function. So f of. Now, remember that everything works backwards inside the function, so if it's a horizontal stretch of 1/2, we want to multiply by 2 inside the function. Now, if you're thinking, I was looking for that number under here, you could have done that 1/1/2, like this. But we don't like fractions within fractions, so just think of this. We're dividing by 1/2, or we're multiplying by 2, and so that just simplifies to this right here. Now, what's our mapping notation? X and y gets mapped onto. Now, mapping notation matches our verbal description. So we just want 1/2 x, and nothing is happening to the y's. We want to horizontally stretch this graph so that it passes through the point 3, 0. We can't use any other transformations, so we can't just slide it or translate it to the right 1 unit. We've got to horizontally stretch it. Now remember, horizontally stretching happens about the y-axis in this course only, so it's getting stretched this way and this way. So if we stretch this over to 3, 0, we're going to stretch this over to -3, 0. And this will not move because it doesn't get stretched at all. So our new graph will look something like this. Okay. Draw the new graph, done. Find its equation. So I actually know the equation of this one here. It is -x². From the vertex it goes down 1/1, so there's no stretch there. And it's negative because it opens down. And a +4 because the vertex is up here. So I can write the transformation in function notation using the f of x. And that would be something like this. We have y is equal to f of. And there's a horizontal stretch, so that means we're working inside the function. So I'm going to use a b for that horizontal stretch. And Just need to figure out what that b is there. So I'm going to change it to this with the actual x's, so then I can work with it better. So y is equal to, wherever I see an x, I'm going to replace it with bx. So this will be negative bx squared plus 4. Now I just need a point on the graph. How about the point I was aiming for, 3, 0? And then I can solve for b. Okay, so I'll just do some algebra. I'm going to add this 3b squared onto the other side. So 3b squared onto this side. And that equals 4. Then I'm going to, looks like, square both of these. So 9b squared is equal to 4. Divide both sides by 9. Get b squared is equal to 4 divided by 9. Square root both sides. And I get plus or minus b is equal to 2 over 3. Now I look at this and I don't want a negative. If I had a negative inside here, that would be a reflection, and it would work, but the question says no other transformations, so I don't want this negative because then I would have a reflection with it. So I'm going to cross that out. I'm just looking for the positive value here, just to give us a stretch alone. So my b value is 2/3. That means that my equation here is y equals negative 2/3 x squared plus 4. And I can clean this up a bit if I don't like that inside, but this is okay for an equation. Mapping notation. Mapping notation starts with x, y, and where do all the xy's go? Now remember that this is opposite of our verbal description and our mapping notation. So when we do mapping notation, it's actually x over b, and nothing happens to the y's. So in the function, we multiply by b, and in mapping notation and our verbal description, we divide by b. So let's put in the 2/3. And we got to clean this up because we don't like fractions on fractions. So x, y is mapped onto 3x divided by 2y. Now this actually works. We could try it using this point right here, 2, 0, that we wanted to transform. And if you put 2 in here, 2 times 3 is 6, divided by 2 again is 3. So this indeed does transform this point to this point here. So it works. So that was mapping notation and the invariant points, and that would be up there. So invariant point would be 0, 4. To summarize all the reflections and stretches we talked about, if we multiply by negative outside, that's a vertical reflection over the x-axis. If we multiply by negative inside the function, that's a horizontal reflection in the y-axis. Remember, this affects the y values outside. This affects the x values inside. Multiply by a outside is vertically stretched by a factor of a. Nice and easy and straightforward. And this is the problematic one. If we have a b in here, this is a horizontal stretch by a factor of 1 over b. Our verbal description is opposite of what we see in the equation. This was part of Relations and Functions 3, 4, and 5, demonstrating an understanding of horizontal and vertical stretches, and also an understanding of the effects of reflections. Here's some questions from the textbook. Give them a try, see if you know what you're doing.